These are your 4-3A notes. 4-3 involves solving quadratics by factoring. So what I do is I try to go over factoring again. I know it's not your favorite topic in math, but I'm hoping maybe by breaking it up, we can remember a few things from Algebra 1 and geometry to help us be strong at factoring. So I think a lot of our issues involve just the word factoring. So understanding what I mean when we say to factor, what that really entails. So what is factoring? It's writing a number as a product of its factors. So you understood factors back when you were in elementary school, and so we just play off of that word. The undoing of multiplication is factoring. So it's taking the number apart and writing it as a product, not as a sum, but as a product, a multiplication problem. So I like to understand or introduce factoring using numbers, and then we get into the crazy polynomials. So when we factor numbers, you write the following as products of its factors. A couple different things. 10 could be written as 1 times 10. That is a fact. They are factors, but it really didn't change any. So writing 10 as 2 times 5 would be considered writing it in factored form. For 15, 3 times 5 is the factored form of 15. And then 36 actually has more than just one factored form. It has several factored forms. So we could write 36 as 2 times 18, or 3 times 12, 4 times 9, and even 6 times 6. And so the bigger the number gets, the more factor possibilities you have. So actually we come into this term called prime factorization to break it down where you can't break down any of the factors anymore. So 10 in terms of 2 times 5 is in prime factored form because 2 and 5 are both prime. 15 written in prime factored form is 3 times 5 because 3 is prime and so is 5. But 36, we have 4 different answers. Rather than having me read off 4 different answers and wondering if we're correct, or even more solutions, the bigger the number gets, the more factors it could possibly have. We need to break these factors down more. Even though 2 is prime, 18 could be written as a product of its factors. Even though 3 is prime, 12 could be broken down more, 4 and 9 can be both broken down more, and 6 and 6 can be broken down more. And what I mean by broken down is that I could write 6 in terms of its factors. So I just want to show you a couple of ways we did this. We used to call them factor trees, and I think they were kind of fun when you were in middle school or in elementary. So to take 36, I could make a factor tree of 36 and break it into 2 and 18. Every time you have a number that can be broken down again, you keep going. So 2 is done, but then 18 can be broken down to 2 and 9. Oops. And then that 2 is done. And then we can break 9 into 3 and 3. And now we have the prime factorization of 36, which would be 2 times 2, or 2 squared, times 3, which would be 3 squared. So either way, 2 times 2 times 3, that's kind of the expanded form. If I took 36 and I decided to break it up into 3 and 12, this 3 is done. I could break 12 into 4 and 3 or 2 and 6. It doesn't really matter. And then the 6 could break down to 2 and 3. So in the end, when you're done breaking them up, I still get 2 squared times 3 squared. Another one that I showed up above was 4 times 9. So I break 4 and 9. 4 can break down into 2 and 2. Those are done. And then 9 can break down into 3 and 3. They're done. They can't factor anymore, and we still get 2 squared times 3 squared. And the last one that I could show is 6 times 6. The first 6 breaks down to 2 and 3. The second 6 breaks to 2 and 3, and they are completely factored. And not only, it factored to the same amount. So I just showed you 4 different ways to give me the prime factorization of 36. In the end, we all got the same answers, just your work looks a little bit different. So I want you to keep that in mind when we're factoring in this section with polynomials. When we have a quadratic equation and you have variables involved, you could do it differently. There's several different approaches. Your work may look different, but in the end, we should all get the same answer. Sometimes a problem or a number requires that you factor again. Other times, you're done after the first step. So that's why I like to use numbers as a reference. You're writing it as a product of its factors. And if you notice, every single one of these, you could check your answer by actually multiplying the factors together and you get your solution. So if I multiply 2 times 5 together, I get 10. 3 times 5 together, you get 15. And 2 squared is 4 times 3 squared, which is 9, gives you 36. So that's another thing that will apply when we're factoring polynomials or quadratics, is that you can check your answers by multiplying it back through. So several different ways to factor, and it just kind of depends on what type of quadratic you're dealing with. So the very first type of factoring we always talk about is taking out the greatest common factor, or the GCF. And that means that every number in the actual problem has something in common, and so we can actually take that out. It's like someone distributed it. We're going to undo the distribution. So we always look for this first. It makes the numbers much more manageable, makes them smaller. So it's always the first type of factoring. You simply divide each term by the greatest common factor. Because in order to get that solution, somebody multiplied that GCF through. So we're undoing the multiplication, and we are actually going to divide them. So what your solutions will look like is you'll have the greatest common factor, a number, sitting on the outside of a quantity left over. And so you could always distribute that if necessary to check your answer. So you're looking for the biggest amount to take out. So if you look at the first problem here, I see that I have a 3, a 4, and a 1. They have nothing in common, but the variables have something in common. The first one, the second one, and the third one all have S's. Now, the first one has 2 S's, but the other 2 only have 1, so we can't take out 2 if we don't have it. So the biggest amount of S's we can take out is 1 S. And then the T's, same thing. They each have a T, but the first one has 1, the second one has 2, and the third one has 3. We're not looking for the biggest amount total. We're looking for the biggest amount in common with all of them. So since they at least all have a T, we can take out a T. So I'm going to put that on the outside. That's my GCF. And then I'm going to actually write divide by ST, divide by ST, and divide by ST. Now when we divide, really what happens is you have an S squared on top, which is really an S times an S, and an S on the bottom. One of those S's cancel because it turns into a 1. And then the T on top and the T on the bottom will just cancel out. So we still have a 3. We'll have an S, but we lose one of our S's in our T. In the second term, we'll have a 4, a positive 4. The S's cancel out, and then a T squared over a T. I have 2 T's on top, 1 on the bottom. I'll have 1 T left over when I divide. And the third one, I'll have the S's cancel. I have 3 T's on top. T cubed is really T. Over a T, I'll actually have T squared left over. So there's a 1. Even though there's no number left over there, there's always a 1. So I have 1 T squared. I could check my answer by distributing the ST through, and I should get the original problem. In number 2, when you look at number 2, I see 24 and 18. So between 24 and 18, I want to take out the biggest number that they have in common. Now I know that that is 6. Okay, I know that it's a 6. And I also can see that they both have A's. But I can only take out 1 A because the second one only has 1 A. And they both have B's, but I can only take out 1 B. Sometimes you can take out squareds and cubes if they each have it. So my GCF is 6AB. Now what I want to do real quick is I want to pretend that we didn't know it was 6AB. Maybe you saw this and you thought it was 3AB. You saw 24 and 18, and so you thought it was 3AB. On purpose, I'm going to factor this, take out a common factor, just not the biggest one, because this will happen, and I want to show you how you fix it along the way. So instead of taking out the 6AB, let's pretend just for this problem, that we thought 3AB was the largest amount that they had in common. So I divide by 3AB, I divide by 3AB, I pull the 3AB outside. It doesn't go away. You can't throw it away. You have to be able to, you're writing it as a product. All your answers should be multiplication problems. 24 divided by 3 is 8. The A's cancel, leaves me with an A, and the B's cancel out. So I have 8A left over. Negative 18 divided by 3 is a negative 6. The A's cancel out, and then I have B squared over B, which will leave me with a B. So when I look at this, I did take out a common factor, but just like our factor trees, 3AB is done, but if you look at the remaining factor, 8A minus 6B, they have something in common. I could take more out. And we know this because we actually know the true GCF is 6AB. So I'm going to take out, rather than starting over, I'm just going to take out what I missed. So what's in common, what's a common thing that goes into 8 and 6? It's 2. So if I divide by 2 now, it still needs to come outside. So the 2 and the 3 make 6, and there's our 6AB. So you don't have to start over. It's just whatever other factor you take out, you just multiply by the original factor that's there. When I divide 8A by 2, I'm left with 4A, and a negative 6B divided by 2 leaves you with a negative 3B. So this right here is my factored form of that first number. When I look at it, I always check inside to make sure there's nothing else in common between these two. So that's factoring by greatest common factor, GCF. Now we have another one that uses greatest common factors, but this method of grouping applies when you can't find a number in common with all the terms involved. So if you look at number 3 here, I see an A in all of them but the last term, and so I can't take an A out. I see 2's in 2 of the terms, so I can't take that out, and a couple of them have B's. But there's nothing in common besides 1 that I can take out of everything. So I couldn't use greatest common factor. So this is where you'd use grouping. So one of the clues that you use grouping is when you have 4 or more terms, but they have to have an even amount. You have to be able to put them in even groups. So if I split this number, this 4-termed polynomial, into 2 groups, there'd be 2 terms in one group and 2 terms in the other. So that's when you use grouping. You split it into 2 equal groups, and then you find the GCF of each group. So you factor out a greatest common factor between the 2 terms and then the other 2 terms, and the remaining parts should match. And then you rewrite it as a product of 2 quantities. So your answers here will not be a number on the outside. It'll be 2 quantities, like 2 binomials or 2 trinomials. So when I factor, I'm going to break it into 2 parts, and so I'm going to split it right down the middle. Or you might want to just make it a little jaggedy split so that you know that that's not a 1. And so I'm going to look at just this first part and see what I can take out, what's in common between those two. I notice that they both have an A. So I'm going to divide by A, put A outside. An A squared divided by A leaves you with an A. And a negative 2AB divided by A leaves you with negative 2B. Okay, now, when I factor the other side, I better get an A minus 2B or I did something wrong. So when I look at what's in common between A and 2B, really there's just a positive 1 that they have in common. So I'm going to take that out. Positive 1, put your plus 1 there. It's really important to put the sign. And when I take 1 out of A, I'm still left with an A. And when I take 1 out of negative 2B, I'm still left with negative 2B. So sometimes you have to factor out a 1. It's the only thing that they have in common. But what I want to point out here is that this remaining term, A minus 2B, matches this one. If they don't match, this is where you know you did something wrong or this factoring doesn't work. Since they match, that tells me that A is being multiplied by A minus 2B, 1 is being multiplied by A minus 2B, so therefore we can say that A plus 1 is being multiplied by A minus 2B. So you take those 2 outside numbers, put them together in one quantity, and then rewrite the A minus 2B once. So rather than saying that each term is being separately multiplied by A minus 2B, I just combine them and say they're both being multiplied by A minus 2B. So this is your answer. So your answers to grouping will look like the question to a FOIL. To check that, you would FOIL. Part 4 here, or number 4, if I break it down the middle, I look for a GCF. There was nothing in common with all of them. I can see that on the first group, I can take out an x. I'm going to divide by x, x outside. I want to see this work on your homework. Eventually, we'll get rid of that, but right now, as we're learning, I want to make sure that you show all that work. That leaves me with an a left over minus b. So I want to make sure I get a minus b on this other side. So I'm going to divide by y. They both have a y in common, and put a positive y out in front. And that leaves me with an a minus b. Notice that the a minus b matches this a minus b, and so I can put the outside numbers together. So since x is multiplying a minus b and y is multiplying a minus b, I can say that x plus y is multiplying a minus b. So there's your solution. It's the same thing in factored form. Factored form means it's written as a product of its factors. I could FOIL that to check my answer, but I'm not going to do that. So, your summary. Explain to me why the factored form 2x times 4x minus 6 is not correctly factored. That is not the correct answer. And then I need you to factor that trinomial. Good luck.